particular star clusters. She has done important work in understanding star clusters outside our galaxy, so as a tracer of star formation in other galaxies, and going further and further up to the point where she is now, where she's leading some of the best surveys with JWST that really look for clusters at very high redshift. She has found some of the highest redshift clusters ever detected, a redshift larger than 8, which have been in the news a lot in the last months, published on Nature. And let me just tell you that Angela started out as a PhD student in Stockholm, and she got a PhD there in 2011. Then after that, she went on a postdoc at NPIA Heidelberg, and then she came back to Stockholm with a national fellowship, and then she stayed over there, and she is an associate professor at the Oscar Klein Center at the University of Stockholm. And today she will present us what she has found on star clusters near and far, the little sparks in tracing galaxy evolution through cosmic time.
Thank you very much, Lucio. And thank you very much, everyone. It has been really nice to meet you in the coffee area or in the corridor and chat a bit with you during group meeting. Pedro didn't tell me that this is a theoretical seminar, so it's going to be essentially 90% on observations. And I hope to tease out of you some interest, since that hopefully will inspire you to do some theoretical work then on this. Yes, so also I have to say before I start that this work is done in collaboration with some very close collaborators and friends. Adelaide Clessans was a postdoc until end of last year with me in Stockholm. Now she's a researcher in Lyon. And then Mirka de Savansky, maybe you have met her. She has been visiting here. I believe she's in Geneva. And then other collaborator, Matteo, Eros, and the Spring collaboration, which is like more than 100 people, so it doesn't fit in the page. But everyone has contributed, because you will see we need a lot of expertise, not simply on star formation, but also on techniques that are really beyond one person expertise. So as I told some of you, my main interest has been, yes, I think all of you are acquainted with the vision of this figure. Here you see essentially this is the one we recently published after the EC Breakthrough Workshop review we put together. You will find this review with my name, but I want to stress I do not take credit for the review. This was a work of 40 people. And if you want to read more about recent observation and result, please have a look at that. And in particular, I put out this picture to kind of guide you where we are in the universe. I will not talk a lot about the very local universe, but essentially it will be the starting point, because when we look at the local universe, and here I put one of the images of the galaxy we are studying in my group. This is a first observation done with JWST of the Whirlpool galaxy, M51. And you are seeing now the ISM of the galaxy together with the stars. Essentially, when we look at local galaxies, we know that there is a regulation in the star formation process. So galaxy in the local universe, on average, star-forming galaxy in the local universe are forming stars in a regular matter. So we have gases collapsing, forming dense core, in the dense core forming stars. Feedback from stars inject turbulence in the ISM and prevent too much star formation to take place. And that's how galaxies sustain star formation over giga-years time. Now, of course, we studied the details at very high physical resolution in local galaxies, and we wish to do the same at high redshift, but this has not always been easy. Now, if you look again at this map, every bright point here is roughly 1 parsec in physical scales. But when we look at the universe, and for instance, we use one of the best instruments until 3 years ago, Hubble, would give the sharpest PSF, what we would see is the galaxy roughly around the redshift 1 to 2 look very clumpy. We didn't see any more regular morphologies. And there was a huge field looking what was happening to these galaxies. And actually, thanks to the study of these clumps, we understood that the galaxies already at the peak of the cosmic formation history are not as peaceful as our local galaxies. They are forming stars at much higher rate, and they are forming stars in these big clumps. So clumps would be these enhanced point sources that look like, yeah, they look like clumps essentially. And during the last, during 2000, 2010, what was established is that, yes, galaxy morphologies are changing. The clumps dominate the UV appearance. So we knew that they were young. A fraction of them are star forming. They are stellar structures within the galaxies. And if you took M51, I showed you before, you will smooth the resolution. M51 will not look like any of these galaxies. So the star forming region in this galaxy are different. And more, we can say, so these are in place, but below redshift 2, and then so to understand how these clumps form, essentially we looked at these instabilities or these stabilities theories, and I found out that this must be really unstable. So essentially fragmentation is taking place over disk size. So it's not taking place into clouds, but the entire disk is unstable against collapse and will fragment, creating these big clumps. I think one important result also that came out in 2016 is that the fraction of light in galaxy in clumps seems to increase as we go into cosmic noon. And so the result of this essentially analysis here from Shibuya would suggest that the clumps at cosmic noon are forming out of fragmentation or in situ within the galaxy, while clumps at higher redshift are more likely to be driven by merger, and maybe the multiple clumps we are seeing are multiple satellite galaxies coming into these small galaxies. With the Mirka, this was long time ago, 2018. Essentially, at that time, we collected all the clumps of which we knew masses, and we looked at the mass function. And you see that between redshift 1 and 3, the mass function of clumps in galaxies, so here is not one galaxy, we combine the clumps of the galaxy population we could look at. It's essentially close to a power law -2. And you know better than me, essentially, if you have a turbulence and turbulence is organizing the density in the medium, and then you have collapse, fragmentation and collapse, you will form a mass distribution that follow a power law -2. So essentially the mass function of the clump population at cosmic noon is indeed showing that there is in situ formation for these clumps. And then a lot of open questions are still there before JWST came online. So here you see this is a set of simulation of isolated disk by the group of Bourneau et al. And there you see essentially they show the morphology of their simulation. And in the bottom row, they are showing real galaxies in the deep field, the Hubble deep field. And they say, okay, we got right their morphology. The UV looks like these clumps are youngest are forming, while the mass of the galaxy, which is the orange image in the simulation, coincide with the mass distribution in the filter in the H-band HST, which is showing where is the stellar mass of the disk. So essentially, they concluded that clumps form in gas-rich galaxies. So if you have a high gas fraction in disks, you can fragment and form massive clumps. But then there were still questions unanswered. And I think here Valentina Tamburello, together with Lucio, pointed out that actually simulation had still a big step to do, because Fibbe prescription actually matter a lot in the way clump form, and survive. So we cannot say, so at the time in 2014, it was kind of, okay, these clumps are the units of star formation for this galaxy. They will migrate in the center and form the bulge. But actually it's not true if you don't account for all the physics. So simulation were showing something, but this was not yet really supported by observation. There were tentative evidence of clump migration. And remember, we were seeing only a fraction of the light. JWST was not there. So before JWST came online, I think many questions were still there, and we were discussing. But I remember we were in Munich for a long workshop. I think something important is also that we were looking at low resolution. But when you use lensing, and you use gravitational lensing to distort and magnify the light of galaxies, actually you don't see anymore the kiloparsec scale clumps. They are actually not units because they break down into smaller units. Star formation is hierarchical, and when you resolve clumps, you can see within them. So already with JWST, this became more clear. So we see essentially that if we look at the highest magnified galaxies, so in the arcs, we are reaching very high physical resolution, and we are reaching scales of star cluster. We are looking at 1 parsec, 2 or few parsec scale stellar objects that probably are gravitationally bound. So you see here, we had many single case studies, but also people start to gather samples, and something that came out clearly that there was a tendency with redshift to look at more and more extreme star forming regions and the star forming clumps within galaxies. So now we add JWST, and we actually extend our studies of clump structure down into the beginning of reionization. And what we see with JWST, I thought it's interesting to connect the small physical scale with the galaxy physical properties. So the first, I think, important result at the galaxy scales is actually the disks are in place already much earlier. And this is, we were not capable of seeing this because we couldn't see the optical light of galaxies beyond the redshift 3. But now we can, and we find the disks already at redshift 6. And then another important thing is the dynamical feature, like the presence of bulge. The bars are already there much earlier than we thought. Already at redshift 3, we can find a significant fraction of this structure in galaxies. Another important result, so here I'm showing you the comparison between the galaxies that we knew before JWST and redshift beyond 6. And you see it was just a few tenths up there, the little blue dots. But now we are looking at a population of galaxies for which we know exactly the redshift. We get spectroscopy, we can study their physical properties. And what the universe is showing us, that there is very little constancy in the way stars are produced. And this is especially true for early galaxies, where we are looking at galaxies essentially that are forming their first generations of stars after POP3. So we are not yet seeing the POP3 galaxies, but these are galaxies that are like 10 to the 7 solar masses. So they are really starting building up their mass. What can we say about this galaxy? For instance, we can see that their sizes are becoming increasingly compact. So they are becoming smaller and smaller. Of course, this is kind of intuitive, right? But then when we look at the physical properties, so this is a study that came up last year. The plot is showing the distribution of equivalent width in oxygen 3 plus H beta. The strength of the equivalent width in these lines is telling you how strong is star formation taking place in the galaxy with respect to the stellar population underlying in the galaxy, okay? So, and what people see when they divide the sample based on the luminosity is that the brightest galaxies, the one that are causing the star formation rate density, the cosmic star formation rate density go up with respect to the constant line. If you remember some of the previous plot, they're forming stars at a very crazy speed. While galaxy in the fainter luminosity, so now this is the very end of the luminosity function in the UV, and these are the bulk of the galaxy, there is a mixture of equivalent width. So either they are in a bursty phase, or they are off phase burst, or they are metal, their metal enhancement is changing because oxygen is really sensitive to the metallicity of galaxies. But essentially, you see that at the very faint end here, the spread is the largest. And this is clearly a combination of off-burst and as well as mass. Very low mass galaxies can have a powerful burst, but yet be very faint. And the connection then with ionization is that this type of galaxies are the one then producing the ionizing photons. Here you see the Xion values for a galaxy as function of redshift. And we see essentially that galaxy seems to become more and more efficient as we look into cosmic ionization. Again, this is just an efficiency of producing ionizing photons. Then you have to get them out of the galaxy into the IGM of, so even outside of the circumgalactic medium to realize the universe. And finally, when you combine, so this was a very interesting study that has been done. They took all the spectroscopy of galaxies known above redshift 4, so between redshift 4 and 10, and they stacked them, creating representative properties, physical properties of galaxies. And the stack was done based on the strength of the equivalent width. So as we go in this direction in the plot, we see the average UV spectrum of a galaxy that is increasingly older, a galaxy population that is increasingly older. And what they see is essentially that the average population is dominated by star formation. So this is like a UV BPT diagram. If the points would have been down in the, where is the red clouds of dots, then they would be dominated by AGN, but actually the average galaxies in these redshifts are dominated by star formation. And also, since it's spectroscopy, you can look at composition, metal composition. And here you see now that the average galaxy shows some enhancement in nitrogen. So when we look, and this is really interesting because then it folds up a lot of implication of what type of stellar population are within the average galaxy at high redshift and how nitrogen enhancement is produced. We will come back to nitrogen later on. I will explain it a bit better. So, and finally, what we see also is before we had the blue cloud, we knew of the population of quasars. We knew that they were really bright, but actually JWST has now shown in the same redshift has allowed us to reach the faint AGN population. And surprisingly, it seems that the black holes in galaxies at redshift between 4 and 10, let's say, are overly massive. They can be up to 10% of the galaxy mass. And here you see the bottom, the gray dots show the local universe relation. And then all the JWST results, the red dots are, these are not all little red dots, but they are red symbols, are sitting above. So what is happening? So there is a lot going on, which I cannot summarize here really, but people are thinking that probably black holes are creating at Eddington or even super Eddington rates to be so massive. And then maybe the galaxy will catch up later and form their stars later, because this is really surprising. And there is there is a lot of work also about what type of black holes are forming. So then we have really to look much back and understand where the black hole seeds are coming from. Are we looking at the light seeds that grow as super Eddington until they reach redshift 10, 8 that we are seeing now, or we are starting from heavy seeds, maybe like direct collapsed black holes. And then maybe we don't need the super Eddington accretion to explain the observation that we are seeing here. So this is all going on. There is a lot also now in the literature in this week, which I am not reporting. Is the field is changing too fast to really keep up. But this gives you a bit an overview of where we are in terms of galaxy properties. And of course, now we go back to the clumps, and we are seeing essentially that as we look with JWST, we can look down to redshift 10, so we can look at structure in galaxies already a very high redshift. And what we see is that disks, probably not well-shaped spiral arm, but these galaxies are already in place much earlier in the universe. And if we can resolve their sizes, essentially we can find within them star forming region and the star cluster. And we will talk now for the rest of the talk of the properties of this at the smallest physical scales. Why WST is so important? I thought since most of you do theory, it's a bit difficult to really understand why it's so important. So essentially, when you have HST and JWST together, you get the best physical properties at redshift 1 to 4 because you cover from UV to near infrared. And then you can break all the generacies, you understand their extinction, you understand what is the age and masses of the little clumps and star cluster. While when you go higher redshift, you have UV and optical, again, you get secure age, mass, and extinction. And then as you go at higher and higher redshift, you go from robust to good. So it's a fair estimate of the physical properties. But remember, we are seeing mostly the UV. And the UV is tricky because it fades fast. So we actually, when we report the properties of stuff at redshift above 7, we are telling what is the UV average properties that we are discovering in this galaxy, unless we add the MIRI. And the MIRI, of course, the resolution is worse. So for what regards studies of clumps, we have not yet introduced MIRI. So we see this is what we are gonna cover in the next 20 minutes or so. So the first result I would like to focus have been obtained in the galaxy cluster field Abell 2744. This was the field with most hours of JWST observation so far. So it's more than 500 hours. And there is a huge amount of data. And here you see we have combined observation of the uncovered survey, which are the broadband filter, with the medium band filter. You will see in a second why this is so important. So this is like the press release. Unfortunately, it looks better on my screen. And, and this is work that we have done with Adelaide. You see here the morphology of galaxy. We are looking, these are all lens galaxies. When you see that they look more shear, this because magnification is higher. When they are like this spiral galaxy at redshift 2.6, has actually magnification in both directions. So the morphology is kind of preserved. And what you see is as you move at higher redshift, we are looking at, at the beginning, we knew that the clumpy fraction is going down. So the number of clumps star forming region or stellar structure within this galaxy becomes smaller as we move to higher redshift. What do we do? Essentially, let's take the galaxy here on the left side. And you see all the little dots, we model them to derive the light, the size of them and their light. And then you see we create a model in the image plane and we subtract it. And these are the residual, it's the leftover light of the galaxy. And then since we can recover the fluxes, we can do SED fitting and determine their physical properties. Then what happens when you have a lot of filter, broad and medium bands? This is a clamp, an SED of a clamp. And you see that when you have the medium filters and when the emission line ends up in the medium filter or in the broad filter, you see jumps. And this tells us essentially what is the age of the clamp and what is the extinction. So we determine robustly the physical properties of the clamps in galaxies. And you see, this is the mass distribution we get from the galaxies that we have collected in number 2744. The majority of galaxies are lower mass because those are the majority of galaxies in the universe. And the lensing actually let us see this population while we are low in number of very massive galaxies. And here you see now the clumps. We see the physical properties. These are the absolute luminosity of the clumps as a function of their size. And we provide here contours of another data set, but essentially we are reaching physical scales of 10 parsec in the clumps in ABER 2744. And you can see also that there is this evolution here with luminosity, and this is simply due to completeness effects. So when we look at the properties of galaxies and the mass of the clumps we derive within them, we see essentially that the clumps are really massive structure in these galaxies. They tend even to dominate the galaxy mass. And when we do look at their ages, median ages, essentially more massive the galaxy becomes, older the clumps are in this system. The other plot on the right side is showing you the fraction of mass in clumps with respect to the total mass in the disk. You see there are some galaxies seems to have more mass in clumps than in the galaxy. This is because of the uncertainties in the SED fitting, the way we sample the star formation history. But on average, when we look at the population, we are seeing that galaxies with lower specific star formation rate, so galaxies that are forming less of their mass in the disk, have actually lower mass in their clumps, while galaxies where they are forming the bulk of the mass in their system have a higher fraction of clumps within them. This is done at a ratio between 1 and 5, you are seeing. Yeah. So we are moving a bit away from the cosmic noon. We are looking at the average population up to ratio 5. And yes, here I think it becomes a bit more clear. So, sorry, let's... yes, go ahead.
So do you also count, let's say, if there's a bulge or something, do you count this as a clump as well?
So
with a single clump, is that...
Thanks for that question, because I forgot to mention it. So we actually, in this plot, we removed the central clump because we don't know if the central clump is already a protobulge. So what we are looking here is the mass of the second most massive. Usually the one in the center is the most massive. So we are looking at non-central clump here. So the most massive are the non-central clumps.
Central clumps are the gray dots.
Yes, the central clumps are the gray dots, and essentially they kind of follow. But if we would use the central clump, the median, I will go a bit up. And then here you see again the age of the clumps. Now we divided the top row. You see the sample is divided in redshift bin, and the bottom row is divided in galaxy mass. We can do that because we have a large sample. So you see that as clumps, we move to higher redshift, clumps on average are becoming increasingly younger, and they do so at all distances from the center. And if we divide it in mass, we see essentially that the most massive galaxies are the ones which on average have older clumps in them, while the low mass one, the clumps are very young. In the other plot, we are plotting the fraction of mass in clump versus the total mass of galaxies, divided again as a function. This is now every single clump here as a galactocentric distance from the galaxy. And you see again that the fraction increases as a function of redshift. So as we look at lower mass galaxies or at higher redshift galaxies, the clumps dominate the stellar population, the stellar mass of the galaxy. I think one more thing that we can say regarding this migration scenario is that on average, we don't see any trends with the clumps becoming older closer to the center, which would suggest that the clumps are forming in the disk and migrating towards the center. The average galaxy is not showing this migration, okay? And this is also very important because maybe clumps are not so long-lived to move to the center, or maybe we are not sampling enough. Remember, we had very few galaxies at masses above 10 to the 10 solar masses. Maybe the migration is an effect that takes place only in very massive galaxies. So it could be an effect. Our sample is biased in this case. We are working on increasing it. So now we are gonna look again at the entire sample, but this time the red histograms is showing you the properties of the clumps in galaxy above redshift 5. So we are focusing now on clumps forming during reionization. You see that on average, the magnification, which is this middle plot, and the sizes, so the magnification are similar, but the sizes are a bit, clumps are more resolved. This is like where we get upper limits below this line. This is simply a cosmological effect. We see higher resolution as we move at higher redshift. Then we look at the mass of the clumps, and we do not see significant changes among the population. These are all normalized distribution because the number are a factor of 10 different between. So we have not so many clumps at redshift above 5. The ages of the clumps are significantly younger. And then we see their stellar density seems to be on average higher. And finally, we see essentially that the star formation rate density, so the amount of stars that the clumps are forming is significantly higher as we move at higher redshift. And the specific star formation rates are also higher for these clumps. So we are seeing a population of clumps that is forming now and is forming a lot of stars at very high rates. We plotted this as violin distributions, and essentially what you see is that we see a kind of trend where the high redshift, the one above redshift 5, which is only a single distribution there, reaches very high densities. We are looking at regions here that are on average 50 parsec across, and their density are on average comparable to globular cluster. So there is an effect of completeness, which is the bottom part. If the clumps are low density, they may be there, but we don't see them. But the top one is really significant because we see all of them above. And you see that the star formation rate, there is a clear evolution with the maximum star formation rate. So the maximum amount of stars you can form in the same physical scales. And finally, we looked at the mass function. And now you see we divided the clumps as function of redshift, and we are reaching redshift 9. And I don't know what I was hoping to find. No, I know what I was hoping to find. But you see that all the distributions are similar. We are not, so we know that these galaxies are emerging like crazy, right? We are looking at redshift 9, 10, 8. We know the merger rates must be high, but actually merger probably is enhancing star formation, but star formation is taking out of fragmentation. We don't see changes in the mass function. we see significant, what is significant here is that the mass of the clumps, the very massive ones, are only in the disks at cosmic noon. We don't see this 10 to the 9, 10 to the 10 in the small galaxies during cosmic reionization. And then finally, how far I am? Oh, okay. I can go here quickly. We are looking at now with the Adelaide at the equivalent width, like they do for galaxy, but now we are focusing on galaxy, on the clumps. And you see the color, the red color, the green, is showing you which are the star-forming clumps, where ionizing photons are produced in the galaxies. And we use essentially the game of medium filter, a broadband filter, to derive equivalent width. So the sample is about a similar number of clumps in both, we do for H alpha and oxygen 3 and H beta. What we see when we look simple at distribution is that the same galaxies, the equivalent width we derive for the galaxy, and then when we look at the clumps, we always see in the clumps on average higher equivalent width. So if we want to look at the places where ionizing radiation is produced, we want to do that using the clumps and not the galaxies. Then what we see again, when we compare the equivalent width of galaxies and clumps, we see, like, you see this line of dots. Those are all clumps, are forming clumps within the same galaxy. So on average, again, the same effect, the clumps have a higher equivalent width. And we see here the line, essentially how it moves, depending which galaxy you are looking at. If we look at the Xion, so the ionization rate production, you see the purple squares are showing the average for galaxies as function of redshift. Clumps at the lower redshift dominate, so they are always above the maximum clump, the maximum equivalent width clump. As on average higher Xion production than the average galaxy, until we reach redshift 5 and above. And there we are seeing the galaxies are becoming smaller and clumps are dominating. So the clumps and galaxy becomes almost the same thing. And finally, we see this effect also here. Now we are, instead of plotting redshift, we collapse and we plot the mass of the galaxy. High mass galaxies essentially are really very poor efficient. So we know they don't form a lot of ionizing photons because their mass is already there. Their star formation rate is a bit lower, while the low mass galaxy are the ones that dominate this production, and the clumps even more.
When you say that the shift now does become the same thing,
yes,
should I understand that it's consistent with the fraction of mass?
Yes, it's consistent with the fraction of mass, the fact that the specific star formation rate becomes the same. So essentially the clump is essentially the stellar population that is forming in the galaxy. Yes. Okay, now in this final, it's just the conclusion. As I said, when we reach the highest magnification, we can look at a stellar cluster. So we can see what happens with stellar cluster. And here, just a quick reminder. These are globular clusters in the Milky Way. We know that they are very old. We know that there are variation in their metallicity. We think that a fraction of this formed in the progenitor, and a fraction have been coming in accreted by the main progenitor while our Milky Way was assembling. The globular cluster stars show patterns in chemical enrichment we don't see anywhere. This is like the first and second population. The second population has show correlation in abundances of sodium and nitrogen. And then we can say it has anti-correlation between the nitrogen and the oxygen and the nitrogen. This anti-correlation of second enriched population seems to be in place already in globular cluster forming down to redshift 0.6. But then we don't seem to find it in a younger globular cluster. It seems that there is also a weak dependency on mass, but this is not clear because we don't know how much mass globular cluster have lost, right? So the mass limit is a bit uncertain. The age seems to be kind of puzzling. And finally, we see evidence of intermediate mass black holes in nuclear star cluster that have survived. So this is omega Cen, and people are also looking at the more normal globular cluster. So why this matters? Because now we can look actually at what we think are the progenitor of protoglobular cluster, or where protoglobular cluster are forming. I'm not saying that this star cluster we see at redshift 6 will survive. We don't know, so the survival rate is really uncertain. But we are definitely seeing how globular cluster formed, the condition. And what we see, for instance, this is the sunrise arc. We find a very compact star cluster. Some of them are already evolved, so we don't see essentially emission line in them, while some of them have a very high equivalent width. So they are embedded, they are covering the star forming region in this galaxy. Their stellar density are very high, 10 to the 4, 10 to the 5. And yeah, we see an evolution in their ages. So they dominate essentially the star formation in this system. This is another object, a redshift 8 now. It's really interesting. It's the Firefly galaxy because the star cluster 10 are associated with the extremely powerful emission line. So essentially to explain the line ratio, we need to assume that within them there are very hot stars, like 50,000 Kelvin hot stars powering, because otherwise you would not see this type of line ratio within them.
You need a top.
So it could be a top-heavy IMF. Unfortunately, they didn't use an IMF of 300 solar masses. They use, it's more top-heavy than 100 solar masses, but isn't unclear. So you need the very massive stars of the type, so like Wolf-Rayet, they can reach 50,000. And it is suggesting top-heavy IMF. And then this is the highest arc we have found so far, where we see star cluster within the cosmic gems arc. And we see, essentially, you see the arc is a double image. So it's the same cluster twice. There is the critical line crossing the arc. And we know also where is the counter image. So the model is quite accurate. We got spectra a couple of weeks ago. So now you see that's our NIRCam imaging, and these are the IFU spectra from NIRSpec. And now you see that within the NIRSpec, there are emission lines. So our redshift actually is not redshift 10, but because of the huge Lyman alpha damping effect, the galaxy is actually a redshift 9.6. So we have now updated all the analysis. Here you see the fit of the emission lines and the galaxy properties. We can fit the spectrum and derive that the galaxy actually is really young still, but the spectrum is compatible with a galaxy which is like post-burst phase. And the burst was very narrow, a few million years. And so the mass weighted age essentially is like 15 million years. It's already quite metal rich. We are at 15% solar. We use the oxygen 3 over H beta to derive this metallicity. So it's just an indication. And when we look at the cluster properties, so this is not a very bright galaxy. It's a UV luminosity of -17, 18. So this is a representative galaxy of the bulk of system we see, a redshift 10 roughly. The star cluster are within 50 parsec, and their masses are roughly 10 to the 6. This property didn't change. The only thing that changed slightly is the age. So cluster A, which is the one a bit detached there, is older with the new redshift estimate, while the other 4 objects, the other 4 clusters are a bit younger. And this is also in the right way, because those 4 are the one producing the H beta and oxygen 3 line we saw in the previous plot. So this is the plot of my paper, which is already old, was just last year. We are plotting the surface density of the cluster we found in the cosmic gem with respect to the bulk of the size measurement in the in the local universe. These are young star cluster, and the gray cloud of dots are globular cluster. And then we added also data in the literature. Essentially, you see that on average, we have tendency, the young star cluster in cosmic reionization seems to be very dense. And this is how the plot, sorry, one more time. This is how the plot changed with the new estimate of redshift and the new analysis. Essentially, we are there. It's a log scale, I know, I apologize. It doesn't show really a huge difference. So essentially, densities stay above or close to 10 to the 5 for this cluster. And it's okay. I mean, we expect if they want to become a globular cluster and they will survive, they have a lot of time to expand and lose mass. So it's not so dramatic that they are very dense. But I think it's eye-opening when we think that we want to look at the stellar population within this object, because at these stellar densities, a lot of things can take place within star cluster. So this is a work that actually Lucio and Floro did recently published, where they, in a simulation, they actually formed star cluster. And you see the simulation actually shows densities that are very similar to the one that we find at comparable physical scales across redshift. So we are looking at star cluster forming now, even in simulation that shows similar properties. So I am wrapping up, I apologize. But what I wanted to say is that at these stellar densities, we can have a massive star mergers within the core. We can have a black hole mergers because the probability of now black hole interacting and growing becomes higher. This has been shown, and is still a lot of people are looking into it. And also the fact that we massive star can merge, or we can produce stars of 300 solar masses, a lot of Wolf-Rayet, may explain the enhancement in nitrogen that we expect to happen. You remember the average population at high redshift of galaxies shows this enhancement. And here it seems the star cluster are probably the right place to look at. I will stop. This is kind of summary of my talk, and thank you for your time. Sorry for being over time.
Time for questions. Some of the young people break the ice.
So one thing I'm not in this field, so I was wondering, how did you figure out that the clusters are not moving in or moving out?
Migration.
Yeah.
The migration. So if migration is a dominant effect, then we were expecting to see it in the average age. When we look at galactocentric distances, we expected to see on average older cluster coming closer to the center. While only what we see is that the cluster, as we move after cosmic noon, they are older. So of course the bulk has formed a cosmic noon, but they are not on average closer to the center. So the fact that the age was flat is telling us that this is not a dominant effect, but we are looking. So there are 2 galaxies, this is in the paper, might show this effect with all the clumps closer to the center, but yeah, 2 out of 450. Yeah.
Questions?
Yeah, so I have a question in a similar direction. So if you look at the book, excuse me. If you look at the global cluster distribution, right, in the Milky Way, so they are essentially concentrated, but they also have some significant differences from the center of the Milky Way. So many of these ones, you say they are within, essentially, really close into the center of this galaxy. So I can understand that some internal processes may expand them, but how do they essentially move to these larger distances that we see?
Yeah, so we are
Like
looking.
body interactions or?
I think it's just, well, in the cosmic gems, most likely they will merge because they're within 50 parsecs and they are very massive in a low mass galaxy, right? But then we have a Hubble time. The galaxy will definitely accrete into something else, or it's maybe at the center of its halo and will accrete of the object. So when you have a merger, you definitely push out star cluster. You destroy some and some will survive because they're moving out of the disk. So that's how they ended up. And I didn't have time. One of the galaxy, the Sparkler, ratio 1.4, shows already the globular cluster out in the halo. So it's a mechanism that will select what will survive, essentially. Yeah.
Questions? Yes.
So you said that you don't use MIRI because of the resolution issue. Do you expect to see some, or what would be the reason to go even more to the right?
So at this redshift, when you move above redshift 7, 8, MIRI gives the optical, and it will be sensitive to the H alpha region and also the I band, and then essentially we will see the full mass of the galaxy, or it will help the blend, divide the degeneracy between age and extinction. So that's why MIRI would be, so to have the optical rest frame would be ideal, but the cosmic gems in MIRI is a blob. we have now imaging. So it becomes difficult to add that flux.
So you don't see the clamp, but you just see one.
Yeah, blob. Yeah, yeah. So
I have a question. So above redshift 6, 7, now we still have just two systems, the cosmic gems and Sparkle, or even that have detected clumps, star clusters.
yes, so we have these two systems. We are looking into GLIMPSE. GLIMPSE is a large program from cycle 3 with the deepest imaging, and we are extending the sample. I'm not allowed to show the plot, but essentially you see this plot here with the GLIMPSE, and now we are combining everything we have done in 3 galaxy clusters. There is not a gap anymore, so it's filling up. We are filling up this density distribution. Okay. And so it's not something special in the cosmic gems.
Okay.
It's gonna be, they are there. There is just a continuous distribution of densities.
So we have a question
For the online audience.
So if you can unmute yourself.
I thought I was, you mute. Yes, okay. Volume, yes, here. Go ahead.
Oh, I think you're asking me to ask a question, yes?
Yes.
Okay, sorry, I couldn't hear in the background was being said. Yeah, thanks for the nice talk. I may have missed some of the details, and I saw that you presented some progenitors of globular clusters in the images, and I was wondering what paths to globular clusters can now be rejected with JWST observations, and which kind of pathways are still tenable, and what dynamical mechanisms might be necessary for forming globular clusters. I wonder if you could just, in simple terms, paint us a picture of how globular clusters came to be in the universe.
Okay, then you give me the grant. No, I'm joking. I think okay, this is still under debate, and the debate is going on for 30 years. What creates the second population? I think we have increasing evidence that probably the massive star products were not Wolf-Rayet, has to be very massive stars, or like I'm talking of 300 or 1,000 solar masses forming within this star cluster that are polluting the gas, and the second population has to form in a gas that is not enhanced in iron. So it has to happen before supernova, core collapse, explode. I think that this is the direction we are taking, but someone else can disagree on this. The formation of globular cluster is taking place in galaxies which are very compact, and there's still a population, therefore their sizes are very compact. This is important for black hole, intermediate mass black hole formation, probably, is to be shown. And yeah, what we can exclude? Nothing. I think we are adding information, honestly. Yeah.
Okay, thanks very much.
The picture of all of the Thomson function.
This one?
The Thomson function.
These are the Clamp mass function. This was for the clamps, but we added the redshift 5 to 9.
I think it has a similar shape compared to the Higgs mass function. And the Higgs mass function is completely gravity effects. And what are the difference between the Higgs mass function and this Thomson mass function?
Yeah, this is the problem of power loss -2, right? We know that the luminosity function becomes steeper. So we know that we are moving from to a steeper luminosity function. So it's a really good question. The -2 slope actually is not helping really to disentangle. We know this fragmentation because we are looking at substructure within the galaxies, but while the -2 of galaxy include all the mass, right, in the galaxy. So for instance, let's take this galaxy here or here. We are looking at the mass distribution of each little dot that we are seeing. So I don't think it's gravity only, because there the baryons are dominating. It must be related to fragmentation, but I'm happy to be corrected on this.
In a way, it is still gravity, because fragmentation.
It's gravity, yes, sorry. It's not dark
Yeah,
matter gravity.
It's not only,
Yeah.
not the collision as
Yeah, so my question is like, how much baryon shape is the shape of the mass function compared to pure gravity?
Since these are dominated by baryons, it's baryons. These are only baryons. They don't contain dark matter.
Yeah, I mean,
What would be the dark matter? I don't know, because they are not combined with gravity. Yeah.
So I have a question regarding the formation mechanism. You didn't talk about too much about this, and I guess it's probably we don't fully know, right? So these, so especially at the highest redshift, so about redshift 6, these are very low mass galaxies, right? And of course, if you go to lower redshifts and larger objects, you can, there we definitely know we have a lot of disk galaxies, and you can go to like tumor instability in the different ways of forming. So I wonder, do we have any insights in how these ones form? Do we, for instance, have some, let's say, kinematic data, so we can say that whether it's like a rotating structure, or whether it's actually not? So do you have some insights?
No, so for the cosmic gems, since now we have I spectroscopy and it's a very weakly emitting, we will never be able to do rotation for this galaxy. For the clumpy structure system, I think it would be really interesting to answer this question. Now we are starting to get more observation of the more compact one, and that should shed some light whether they are rotating or not. Definitely the galaxies that have been looked at with ALMA and with the IFU, these are much more clumpier than this system here. They show rotation. So I don't think that, and also to me, rotation sounds something that we should expect if the gas has to, come in and form stars. I think in your simulation, you find rotating disk as well. Where did you form the star cluster?
We form them in the same way as the lower redshift, redshift 2,
yeah,
tumor instability
But this
type
is,
of regime.
but even with the galaxy that has a stellar mass.
With a very-
Yeah, I mean,
yeah.
because that's the kind of.
Which of course will not work if you have a strong feedback. So I think we are able to do it because we have weak feedback. Otherwise, yeah, I know what you're thinking.
The
Otherwise it would be
ISM,
very- Yes.
Yeah, this is also very interesting
Yeah.
things that it requires further investigation. We don't have all the answer yet. Yeah.
Let's think, Angela, again.